Hi, this is Dr. Cook, your Chem 240 instructor. Let's take a look at the next video.
In the last video we saw a few examples of naming alkenes when I was discussing cis and trans isomers. I want to talk a little bit more about IUPAC naming for alkenes, and here are some examples that we can talk about. So when we name alkenes, what we do is we take the ANE ending of an alkane for the longest hydrocarbon chain that we have and replace that with ENE to indicate the presence of a double bond. So in this case, if we have the molecule shown on the top, this is a 6-carbon chain, 1, 2, 3, 4, 5, 6. So this is a hexene molecule. Now traditionally we have to put the number for where the double bond starts in the chain, numbering from the side that is closest to an end. In this case we number 1 from the left side. So we would normally have called this 1-hexene, but in recent years IUPAC rules have changed a little bit. Formally we call this hex 1-ene, meaning the 1 refers to the point where the double bond starts. Same thing here, even if we put it out in front, 1-hexene refers to that double bond, the ene part, and it indicates the carbon that it starts at. So if we have more substituted groups, we have things like this molecule on the left where we can number from this side, or we can number from, I'll use green here, number from the right side. In that case, if we number from the right side, the double bond starts at carbon number 2, and if we number from the left side, the double bond starts at carbon number 2. So this is, either way we do that, this is a but-2-ene molecule. So if it's the same, or in the exact middle of the chain, where numbering it from either side gives you the same number for the double bond, then you look at the substituents. And so you number from the side of the closest substituent, so we would number in this red direction where the substituent methyl is on the 2 position. So 2-methyl but-2-ene, or 2-butene is how I would have traditionally said that. And I'll probably make that mistake and say it that way a lot, 2-butene as opposed to but-2-ene. Always double bonds get priority over other substituents when naming molecules in terms of numbering. So you always number an alkene, or an alkyne for that matter, from the side of the chain closest to the end, regardless of where there's other substituents. So the double bond gets precedence, and that's kind of indicated here because ene, or the double bond functionality, is actually part of the parent name, not as a substituent in front. So it's part of the parent name, it gets priority. That's sort of a general rule of thumb that seems to always hold true in many cases. Okay, when we have more than one double bond in a molecule, we have to number the positions of their starting points for both of them, and we use a prefix of the ene to indicate how many there are. So in the case of 2 double bonds, you can see we have the diene prefix. And the diene prefix I would have to number from this end to get closest to the branch. So we have a double bond starting on carbon number 1 and a double bond starting on carbon number 5. So this is a 1,5-diene. In this case, 6 carbons long, so it's a hexa 1,5-diene. And there's a methyl group on the 3 position, so that's 3-methyl hexa 1,5-diene. Or in the little bit older naming, 3-methyl 1,5-hexadiene. Either one of those ways to name it I would accept because they are basically being used interchangeably at the moment. Cyclic compounds have similar naming features. We talked about cyclic compound naming in the previous chapter. Again, if we have a 6-membered ring which is cyclic, we call that a cyclohexene to indicate a double bond. And then we have to start numbering from a double bond as being number 1. And again, there are 2 ways we could do it. We could start numbering from this red direction, 1, 2, 3, 4, 5, 6. Or we could start numbering from the other carbon, the green direction, 1. But in this case, the number 2 carbon can't be closer to the chlorine. It has to go towards the other end of the double bond. 1, 2, 3, 4, 5, 6. So you can see the double bond is implied on 1. Notice there's no hex 1-ene here, and that's because with only 1 double bond in a ring, the double bond always has to start at a carbon 1, so it's implied. Now we number in the direction from a starting of a double bond where the number 2 carbon is the other end of a double bond, and you can see if we start in this green direction, the substituent is at carbon 5, whereas if we start from the red direction, the chlorine substituent is at carbon 4, so that's the lower number. So this is 4-chlorocyclohexene. I do want to point out some common names that occur with some of the double bond compounds, and we've used a few of these in class already. So the IUPAC name for the simplest of the alkenes, ethene, is shown here. Ethene is CH2 double bonded to CH2. There's a common name for this which we call ethylene, and you've probably heard of polyethylene, the plastic, and that's a common name for ethene. So it's a polymer of ethene, what polyethylene is. Or polypropylene stems from this propylene molecule, which is propene, but sometimes commonly called propylene. The 4-carbon group is sometimes referred to as isobutylene for some obvious reasons. There's 4 carbons, and remember, isobutane looks like this. An isomer of butane is a common name, and if there's a double bond, it's isobutylene. But the IUPAC name would be 2-methylpropene. And again, since the double bond can only start at carbon number 1, no matter where it is, because it's only 3 carbons, that 1 is implied here. Now, we do have common names also for referring to double bond groups that are attached as a substituent on a larger molecule. By the way, this little squiggly line means that there's something else attached, some larger molecule attached, and this is the bond that attaches to that. So we're just looking at this portion of the molecule when we're looking at describing these things. So when you have a double bond attached to a larger group as a substituent, this is sometimes referred to as a vinyl group. Vinyl. You're familiar with that term because polyvinyl chloride is a polymer, and vinyl records was made from polyvinyl chloride. Vinyl chloride would look like this. That's vinyl chloride. So you see where that common naming kind of stems from. If there's an addition of another sp3 hybridized carbon between the double bond carbon and the substituent that it's attached to, this 3-carbon group we refer to as an allyl group. You'll hear that term used a lot. And there's some special properties of allyl groups in terms of the reactivity of this allylic position that we'll talk about later. And if you have a double bond attached at the end, I'm going to draw the carbon here because it's a CH2. Let's say we're just referring to this group on a larger molecule. A CH2 group double bonded to something larger, so actually the substituent would be here. We refer to this as a methylene because it's a one carbon with a double bond, a methylene. And where might you see something like this? Well, in cases where you have something like this, where you have a larger ring, so this is a cyclopentane, the double bond is not in the ring, and you want to refer to this group hanging off. We refer to this as a methylene cyclopentane in a common naming system. So you might hear this word methylene, and it simply stands for a CH2 double bonded to something else. And that could be many different things. Well, these are the actual formal steps when you think about alkene and alkyne naming. So what you want to do is find the longest chain that contains all the double or triple bonds if possible. So those do take priority over anything else. The double bonds and or triple bonds should be in the same chain. We want to then number the chain from the end nearest the multiple bond. Regardless of where any other substituent is, that's the first criteria. Multiple bonds have priority over any other alkyl substituents or halide substituents. The one exception is alcohols, because an alcohol is part of the parent name. Again, like ene is part of the parent name. When we talk about alcohols, those are also part of the parent name. And we'll talk about that in later chapters. Then we name the molecule using ene at the end instead of ane. And if we have alkynes, that's yne instead of ane. And we can name the molecule based on those. So here's some examples of alkynes. Alkynes and alkenes have equal priority, so whichever one of them happens to be closest to the end, that's where you use your numbering system from. So in this case, we have the 3-carbon group, and notice we've drawn this linear to reflect the geometry of the carbon that's there. Note there is a carbon there, and that's the molecule of with a 180-degree bond angle. This is propyne. So it's the 3-carbon group with an alkyne. The simplest of them is ethyne. That's the IUPAC name. However, this is the common molecule acetylene. You've heard of acetylene torches. Acetylene, this is what's burned because it burns very hot. So acetylene is a common name for ethyne. When your chain is long enough to be able to have different isomers for the position of the triple bond, then again we have to use numbers. So in this case, here's but 1-ine, and in this case, Here's but2-ine. When you have more than one type of group, a diene, triene, if you have more than one alkyne, or if you have more than one double bond, it's diene, triene, etc. If you have both in the same molecule, then it becomes an ene-ine molecule. So in this case, we have an 8-carbon chain where the double bond starts at carbon 1, and in this direction, the triple bond starts at carbon 6. So this is an oct, 1-ene, 6-ine, and that's how we name those molecules. In the next video, I'm going to talk about some ambiguities in our stereochemistry naming system when we use cis and trans, and talk about another naming system that we use to indicate stereochemistry of double bonds.